You're listening to Scientific Giants Who Changed the World. Each episode stands beside one mind and follows a thread of curiosity until it ties to the world we inhabit. Today, we descend into a converted shed on the Rue Lhomond in Paris, where winter seeps through walls that were never meant to shelter precision work. The air tastes of coal smoke and chemicals. A glass tube glows faintly in the corner, not from any lamp, but from something inside it, something that shouldn't shine at all. At a workbench scarred by acid and heat, a woman in a stained laboratory coat stirs a boiling mass with an iron rod nearly as tall as she is. Her hands will ache tonight. They ache most nights now. She is Marie Curie, and in this cold shed, she will make the invisible visible. She will name two elements that rewrite the periodic table, and she will do it at a cost her body will spend decades paying. Begin with what brought her to that shed, because the radiance makes more sense if we know what she was willing to suffer to reach it. She was born Maria Skłodowska in 1867 in Warsaw, a city that had been erased from maps by the powers that carved Poland into portions. Her father taught mathematics and physics in a school that the Russian authorities watched. Her mother ran a boarding school and died of tuberculosis when Maria was 10. The family was educated, pious in a quiet way, and poor in the manner of people who sell furniture to pay for books. Maria was the youngest of 5 children, slight and serious, with a hunger to learn that her teachers noticed and her circumstances obstructed. Women could not attend university in Russian Poland. If she wanted an education that matched her appetite, she would have to leave. But leaving required money, and money required years. She made a pact with her older sister, Bronislava. Maria would work as a governess and send money so Branya could study medicine in Paris. When Branya finished, she would return the favor. For 6 years, Maria lived in other people's households, teaching children their letters and sums, stealing hours after the family slept to read mathematics and physics by candlelight in cold rooms where her breath made clouds. In one household, she fell in love with the eldest son. His parents ended it with the contempt that land and old names reserve for the hired help. She learned what it meant to be bright and useful and disposable all at once. She kept working. She kept sending money. She kept her part of the bargain. In 1891, at 24, she arrived in Paris with enough savings to enroll at the Sorbonne. She lived in a 6th-floor garret, so cold that winter nights she piled every piece of clothing she owned on the bed and still woke shivering. She ate bread and chocolate, sometimes an egg, rarely anything that required a stove she didn't have. She fainted once in class from hunger and cold. A professor sent her to her sister, who fed her and scolded her and could not make her slow down. She finished first in her physics degree, second in mathematics. She was the kind of student professors remember, not because she asked clever questions, though she did, but because she worked with a kind of intensity that made excuses look like a language she had never learned. She met Marie Curie in 1894, introduced by a Polish physicist who thought they might have interests in common. Pierre was 35, 8 years older, the chief of laboratory works at the School of Industrial Physics and Chemistry. He had already made a name with his brother Jacques for discovering piezoelectricity, the way certain crystals generate electric charge under mechanical stress, and he had built exquisite instruments for measuring faint electrical and magnetic phenomena. He was shy in the way of men who prefer instruments to arguments, and he had decided that marriage was a distraction he could not afford. Then he met Maria. They talked about science with the ease of people who had both chosen work over comfort. He gave her access to laboratory space. He lent her equipment. Within a year, he proposed. She hesitated, torn between staying in France and returning to Poland. He offered to move to Poland if that was what it took. She stayed. They married in 1895 in a quiet civil ceremony. She wore a dark blue dress that she could later wear in the laboratory. There would be no white dress gathering stains, no pretense that her life would be anything but work. The laboratory they shared, first cramped university rooms, later the shed, was not equipped for comfort, but it was equipped for patience. Pierre had built electrometers sensitive enough to measure currents so small they seemed like wishes. Marie, who had trained herself to sit still through cold and hunger, had the temperament to measure things that barely whispered. When Henry Becquerel discovered in 1896 that uranium salts emitted rays that fogged photographic plates, most physicists filed it as a curiosity. Marie saw a question worth years. What were these rays? Where did they come from? Did other substances emit them? She set out to measure the radiation from every sample she could borrow or buy, using Pierre's electrometer to detect the ionization the rays produced in air. Uranium emitted rays. Thorium emitted rays. Then she tested a chunk of pitchblende, the black crumbling ore from which uranium is extracted, and found something startling. It radiated far more powerfully than pure uranium could account for. The arithmetic was stubborn. If pitchblende contained only uranium and thorium, it should glow faintly. It glowed brightly. Therefore, she reasoned, it must contain something else, something intensely radioactive, something no one had yet named. Pierre set aside his own work on crystals, an act of faith and love that does not appear on certificates, but weighs as much, and joined her. Together they began the labor that would define them and eventually destroy Marie's health. They would take tons of pitchblende residue, a waste product from uranium mining, and chemically separate it, fraction by fraction, to concentrate whatever made it shine. The shed was a misery. The roof leaked. In summer, the heat was stifling. In winter, their breath fogged and ink froze in bottles. There was no fume hood, no proper ventilation. They boiled enormous pots of ore in acid, producing clouds of vapor that burned the throat and made the eyes stream. Marie stirred the molten mass with an iron bar, her arms aching, her back bent. Pierre measured and recorded. They worked in shifts that lasted until exhaustion made the numbers swim. Between sessions, Marie ran home to care for their daughter, Irene, born in 1897, nursed her, put her to bed, and returned to the shed to check a distillation or read a measurement that could not wait until morning. She did not complain in her notebooks. She described the process as if it were ordinary: obtain ore, dissolve, precipitate, filter, repeat. But the quantities tell the story. They processed tons of pitchblende to extract fractions of a gram. They emptied sacks, filled beakers, boiled away water, and watched crystallizations that took days, while their hands blistered from cold and chemicals. In 1898, they announced the discovery of two new elements. The first they called polonium, after Marie's vanished homeland, a gesture of defiance and grief folded into the periodic table. The second, far more active, they called radium, from the Latin for ray. Both names carried Marie's voice. Pierre insisted she name them, though custom would have let him claim that privilege. Radium glowed in the dark with a pale blue-green light, like a ghost of fire. It did not need a flame or a spark. It simply shone hour after hour, as if it had decided to argue with thermodynamics by producing energy from nothing they could see. The chemistry was persuasive, but the physics community wanted proof. Proof meant isolating enough pure radium to weigh it, to measure its atomic weight, to show it was not an artifact or a contaminant, but a true element with a place on the table. It took 4 more years. Marie led the effort. Pierre helped, but the chemical marathon was hers. She refined fraction after fraction, each step concentrating the radium and removing the barium that clung to it with a stubbornness that felt personal. Barium and radium are chemical siblings. Separating them required fractional crystallization repeated hundreds of times, each cycle demanding days, each mistake costing weeks. By 1902, she had 1/10 of a gram of pure radium chloride, enough to measure its atomic weight, 225, close to the modern value. She had proven its existence with a patience that physicists remember because it is so rare. She had also drenched herself in radiation for years without knowing what it would do. The notebooks from those years still exist, stored now in lead-lined boxes because they are too radioactive to handle safely. The pages glow faintly if you measure them in the dark. Her cookbooks, her furniture, her clothes, all carried the invisible mark of her work. She and Pierre noticed odd effects. Their hands were roughened and cracked, slow to heal. Pierre tied a sample of radium to his arm one night to observe the burn it produced. The wound took weeks to close and left a scar. They thought it was interesting. They published notes on the biological effects. They did not think it was dangerous, not in the sense of a thing that kills quietly over years. The rays were a new physics. Becquerel had found them. The Curies made them a field. Marie coined the term radioactivity to describe the phenomenon, a name so apt that it stuck before anyone else could propose something clumsier. She measured it, catalogued it, and then went further. She showed that radioactivity was an atomic property, not a molecular one. It did not matter if you boned the uranium or froze it, dissolved it or crystallized it. The rays remained constant. That constancy whispered that something was happening inside the atom itself. A hint that the atom was not the indivisible billiard ball that 19th century physics had assumed. She did not shout this conclusion. She noted it carefully, as one notes the first crack in a wall that will later crumble. In 1903, she defended her doctoral thesis, Research on Radioactive Substances, becoming the first woman in France to earn a doctorate in physics. The examiners praised it as the greatest contribution to science of any thesis they had read. Later that year, the Nobel Prize in Physics was awarded for work on radioactivity, to Becquerel for his discovery, and to Pierre Curie and Henri Becquerel jointly. Marie's name was not on the initial nomination. Pierre, when he learned of the slight, refused to accept unless Marie was included. The committee amended the award. She became the first woman to win a Nobel Prize, an honor that should not have required her husband's insistence but did. Fame arrived like an uninvited guest. Journalists wanted to know what she wore, how she kept house, whether her daughter was pretty. She gave terse answers and returned to the laboratory. Invitations piled up, she declined most of them. Pierre was offered a professorship at the Sorbonne and a laboratory, which he accepted because it meant Marie could finally work in a space with heat and proper equipment. But the new laboratory was slow to materialize, tangled in the usual bureaucratic delays, and Pierre grew exhausted by the obligations that came with visibility. Lectures, committees, ceremonial appearances. In a letter to a friend, he admitted he longed to return to the quiet work of the shed, before the prizes and the press. He would not get the chance. On April 19, 1906, Pierre stepped into the Rue Dauphine on a rainy afternoon, distracted, perhaps thinking through a problem. A horse-drawn wagon struck him. He fell, and the rear wheel crushed his skull. He died instantly. Marie received the news at home. She did not cry in front of the messenger. She went upstairs, and whatever sound she made, if she made any, no one recorded. She wrote in her journal, fragments that feel like a person trying to hold on to a mind that wants to fly apart. They filled the coffin and put flowers on it. They closed it, and I could see nothing more. They say he felt nothing, that he died instantly. Why do consolations sound so false? The university offered her Pierre's position, making her the first female professor at the Sorbonne. She accepted without ceremony and delivered her first lecture on November 5, 1906, beginning precisely where Pierre's last lecture had ended, as if the thread of knowledge could not be allowed to break even when the hand that held it was gone. The amphitheater was packed. People came to witness the spectacle of a woman at the lectern. But she did not acknowledge the occasion. She spoke about physics. She taught. She returned to the laboratory because it was the only place that made sense. She pushed forward the work on radium with a focus that looked to some like courage and to others like a refusal to feel. She worked to establish an international radium standard, to purify more samples, to measure more precisely. She also began to collaborate with André de Bierne and other colleagues on isolating polonium, which was even more elusive than radium. In 1910, she and de Bierne succeeded in preparing pure radium metal, not a salt, but the element itself, a shining, soft, silvery substance that glowed and warmed your hand with its own decay. In 1911, she won a second Nobel Prize, this time in chemistry, for the isolation of pure radium. She remains the only person to have won Nobel Prizes in 2 different sciences. The timing was bitter. That same year, a Parisian newspaper published allegations of an affair between Marie and Paul Langevin, a former student of Pierre's. a married man in a disintegrating marriage. The scandal was vicious. The press that had once celebrated her now called her a homewrecker, a foreign woman seducing a French husband. A mob gathered outside her home, shouting. She fled with her daughters to the home of a friend. The Nobel Committee sent a letter suggesting she not come to Stockholm to receive the prize. She went anyway. She stood before the Swedish Academy and delivered a lecture on radium and radioactivity, with no mention of the scandal, no apology, no plea. She accepted the prize and returned to work. The war arrived in 1914 and found her ready to be useful. Soldiers were dying on battlefields for want of X-ray imaging to locate bullets and shrapnel. She designed mobile radiological units, petites curies, the soldiers called them, and drove them herself to field hospitals near the front. She trained operators, positioned equipment, and helped surgeons see inside broken bodies so they could repair them. She enlisted her daughter Irene, then 17, to assist. Together they exposed themselves to radiation repeatedly, day after day, with no protection beyond speed and distance, because lead aprons had not yet been invented and the danger was still being learned. After the war, she campaigned to establish the Radium Institute in Paris, a center for research and for the treatment of cancer using radium's rays. She also traveled to the United States in 1921 to raise funds and accept a gift of 1 gram of radium, purchased by American women through a public subscription organized by journalist Marie Curie. The radium was worth a fortune. She accepted it not for herself but for the Institute. She shook hands, gave speeches, and endured receptions with the weary grace of someone who knows that visibility is the price of resources. Her health, which had never been robust since the years in the shed, worsened. She was nearly blind from cataracts, her hands were scarred and stiff, and she suffered from anemia and chronic fatigue. She continued to work. She mentored students, many of them women who would not have been allowed into laboratories a generation earlier. She ran the institute. She wrote, she measured. She did not speak much about the pain, though those close to her knew she carried it daily. In 1934, while recovering from a bout of illness at a sanatorium in the French Alps, her condition worsened rapidly. She died on July 4, 1934, of aplastic anemia, a failure of the bone marrow to produce blood cells. The cause was recorded as prolonged exposure to radiation. The notebooks still glow. The spoons she used to stir radium salts, the chair she sat in, the doorknobs she touched, all carry the signature of an element she pulled from the earth and held in her hands long enough to name it. She could not have known. No one knew. Radioactivity was new, and its dangers were invisible, cumulative, patient. She worked with bare hands because gloves would have made the work clumsy, and the work mattered more than comfort. She inhaled dust from powdered pitch blende because there was no ventilation, and stopping to build a fume hood would have meant delay. She carried vials of radium in her pocket because it was convenient, because it glowed, because she wanted to show students and visitors the element she had spent years isolating. She paid for the discovery with her body, not in a single catastrophic moment, but in a long, quiet erosion. What do we owe her, those of us who live after the danger has been made visible? We owe her the knowledge that curiosity is not free. We owe her the protocols that now protect scientists from the substances they study. We owe her the 2 elements she added to the periodic table and the field of atomic physics she helped to birth. We owe her the recognition that came too late and too grudgingly in her lifetime. We owe her the memory that she did not do this alone, that Pierre's collaboration made the early work possible, that Irene carried forward the research and won her own Nobel Prize, that a network of colleagues and students surrounded her even when institutions tried to isolate her. But mostly we owe her the honesty not to romanticize the cost. The image of the glowing shed is beautiful, and it should also horrify us. She worked in conditions that would now be condemned as criminal. She was denied credit until her husband intervened. She was harassed by scandal-mongering press when her personal life did not conform. She was dying for years and kept working because the work was the only thing that had never betrayed her. The science she produced is extraordinary. The price she paid for it was unconscionable, even if she paid it willingly. There is a particular kind of genius that does not announce itself with grand theories, but with relentless, grinding labor in service of a single question. Marie Curie had that genius. She took a faint glow in a dark room and followed it through years of chemical drudgery until she could hold the source in her hand and name it. She made the invisible visible, not by accident, but by refusing to stop when the work became unbearable. She taught us that the atom is not eternal and unchanging, but dynamic, decaying, generous with its energy. She taught us that discovery can be a form of self-sacrifice, and that knowing the cost does not diminish the achievement. It clarifies it. If you want a vivid scene that carries her temperament, watch her in the shed on a winter evening. She has been stirring the pot for hours. Her arms burn, her back aches. Steam rises and condenses on the cold walls, dripping back down. The glassware on the shelves catches faint reflections from the Radiance sample on the bench, a ghostly light that needs no fuel. Pierre is at the electrometer, reading numbers by lamplight, calling them to her so she can record them in a notebook already stained and swollen from damp. She is hungry. She will eat later, if there is time. She is cold. She has learned not to mind. She is doing something no one has done before. Isolating a fragment of the periodic table that the Earth had kept hidden until she decided to ask where the glow came from. She does not smile. She does not need to. The work is enough. You have been listening to scientific giants who changed our understanding of the world we live in. Today we stood in a cold Parisian shed and watched Marie Curie wrest 2 new elements from tons of pitch blende. And we learned that some discoveries glow long after the hands that held them have stilled. In our next episode, we will follow a Swiss patent clerk with a thought experiment, Albert Einstein, who will ride a beam of light in his imagination, dismantle the certainties of space and time, and teach us that the universe is stranger and more beautiful than common sense allows. Until then, thank you for your attention and your time. This episode was written as a continuous story for the ear. If it moved you, bring a friend along next time. Until our next hour together, remember that the invisible is not always safe, and the cost of making it visible is not always borne by those who choose to pay it.